you're going from 30 of something, you kind of know each one, to tens of thousands or hundreds of thousands. You don't know them at all. You just treat them as one great big herd of things that you have to manage automatically. In terms of what kind of pressure comes on this thing, and this is also why reliability is the most cool thing you can work on, is everybody is in the cloud, and all the normal names, and then just the health clinics, the police departments, the things that make the world work are also in the cloud. So let me talk about how you build a self-driving cloud, an SDN cloud, something that you don't have to worry about touching. The way we do it is essentially you invest a lot in monitoring, and I'll talk about the monitoring part here. There's many monitoring tools. I'll just talk about two. And then you have to have a scalable service for updating the network. So let me back up a little bit. There's a red line going across the screen. Below that red line is all the hair and complexity of the network, whatever it is. All the optics and the switches and the links and the firmware and all that stuff. Above the red line is the abstractions that you use to reason about and control the network. And we control the network as a graph. We think that's the right way to think about networks and manipulate it as a graph. So then we have a graph service that abstracts the network, and we monitor and update from the graph service into the actual network, physical network. And we use a goal state, GOAL, state-driven model, where you've got an observed state, a target state you're relentlessly trying to get to, and then you propose a move and you try to get there. And there's various applications running on top for building out new infrastructure, for monitoring faults. I'll talk a little bit about that, for moving traffic around, and for checking for any kind of config drift or problem. And it's built to SDN principles. There's a centralized control plane for all of this. Again, centralized logically, but massively distributed for reliability. So what does a data center network sort of look like? These are nouns that you may not use, but you probably have similar nouns like cluster. These are terms that came from our autopilot team. We talk about a pod, which is typically some small set of racks, and then a pod set, a collection of those, which you could think of as the next level of container. And then as you get to a larger group of servers, that's a data center, sheet metal around 100,000 servers. And then those are connected through a wide area network in data center to data center and data center to edge, which reaches the internet and ISPs through things like ExpressRoute. So that's what it looks like. What's on top of it in Azure is all the infrastructure as a service, workloads, the VMs, the containers, and so forth, the platform as a service workloads, the software as a service workloads, Office 365, search like Bing, storage, SQLDB, and so forth, social networks, again, Office in our case, big data. We have a big data offer called Azure Data Lake. And then what is it made of? It's made of servers, NICs, switches, cables, fibers, transceivers, all these things. And controlling those things is lots of individual software elements, the firmware on the NIC and the switch software and so forth, which increasingly, again, for reliability, we're writing ourselves. The theme that I'm going to hit here is that there's lots of components here, which is awesome, because they can fail, and then it's awesome. You've got more. I mean, the design is basically reliable. It can tolerate failure. It's fine. It's designed for small capacity loss if you get a failure. But what happens, what's not so great is gray failure, dropping 1 in a million packets, 1 in 1,000 packets, intermittent issues, and so forth, because you've got lots of elements. And how are you going to find the ones that are flaking out? This is, you build these things out of commodity parts, and even if you didn't build out of commodity parts, there are lots of parts here. And you will have gray failures. So how are you going to cope with them? So I'll talk to you about ping mesh and net bouncer. The one principle is continuous monitoring. So we don't, get an alert, get on call, do something. We just want the monitoring to always run, okay? And ping mesh is a service that runs all the time. So from every one of our servers in the data center to every other one of our servers in the data center, I'll tell you a little bit more about that. There's a TCP level ping going on that gives us a constant reference signal. And allows us to ask, are the paths between a source and destination working reliably? Then we have another continuous service called net bouncer, where if there is an SLA violation, it finds it and says, it's that switch, it's that optical device, it's that thing that's causing the problem. So let me tell you about ping mesh. It's a beautiful talk I heard recently from Facebook on some similar ideas called Net NORAD. This ping mesh we've had for several years, and the idea is that the servers under a top of rack switch can ping each other, and then under multiple top of rack switches at the next level, these servers will ping their friends under different top of rack switches, and then across data centers, you'll also get these ping results going. And so you get this hierarchical, decomposable ping mesh with a massive amount of ping data. Let's see. Here's an example. What do you find? So row here is like a switch, okay? Or it could be a data center, but it's one of these elements in the hierarchy, and a column is the same thing. So switch to switch, for example, or server to server in the data center. So normal, it'll be green. Servers aren't talking to each other, so you'll get white along the diagonal. But in there might be, the occasional drop. That's the little flecks of red there. If a pod set has a gray failure, starts dropping, 1 in a million packets, something like that, and you want to take care of that, then you'll see, if you look at the visualization, you'll see, again, we want the alert to take care of it right away by moving workload off or taking care of the incident. But you can see it in the visualization very clearly that there'll be one, it looks like a flag. There'll be one row and column that'll show red in the visualization because you're having some gray failure event there. It could be just one link or one of several switches somewhere in the pod set. Here's one where there could be one link or one element of the spine having a problem in the data center. Okay, so you'll see this kind of pattern where those little block diagonal green things are saying, the pod's okay, but when I go between the pods, it's not okay. When I go off this block diagonal, I'm starting to see some drops. Maybe 1 in a million packets are dropping on one of the large switches that constitute the spine. So those are examples of how ping mesh shows you immediately that there's some SLA question. Now, you want to mitigate that. You want to go further. You want to find out what it is, take care of it, root cause it, get rid of it forever. But first, you got to find it. So what are we dealing with here? We're dealing with very large class topologies with huge numbers of parallel paths, and they're there for performance and robustness. So they're your friend. All these parallel paths are giving you great performance, but in the case of a gray failure, they're giving you a needle in the haystack type problem, which you don't want. So again, clean failures are awesome. Basically, the network reconverges immediately, and you don't get much disruption. But these gray failures could send you on a kind of an Easter egg hunt for which switch is broken, why is this counter not incrementing, shouldn't it be incrementing, why is the switch swallowing a packet, what's wrong with the optics. And there are many, many possible, it could be the NIC, things that could be happening here, and you have to explain it. And it might just be a low-level degradation, but it'll be persistent. And if you have video applications or big data applications, you'll see this because, like for example, in big data applications, if there's an issue, the big data application will try to spawn more vertices or tasks to deal with the issue. And so you'll actually create a kind of a cascade if you don't take care of the underlying issue. So we want to turn that red to green. Why don't you just use ping and traceroute? Well, there's problems with that. So ping, it's a great tool. The internet is built on ping, but it only specifies the source and destination, not the path. And it's hard to extend. It does cause load on the devices, so you can't go as big as we go with ping mesh, where we have every server, creating this incredible ping mesh, and because it consumes resources. Also, it's just not precise. So what we need is the ability to path control and locate the problem, a ping-like probe, but in band. It should see the same kind of problems that the real traffic sees. So you can think of it as distributed guided probing. If you're a switch developer, you've probably run snake tests, in this port, out this port, in this port, out this port, in this port, out this port. Just do a snake all the way through the switch, and they're awesome because then you can find out exactly if there's any problem in the switch. Back, 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 back like that. So imagine snake testing your entire huge network, millions of paths, and that's what that bouncer does. So the green links here, at the bottom in the left-hand corner, there's S1. They're sending a guided probe upwards to the top, those two at the top, and it can take many different paths, and it's telling it's telling what path I want to take. So there's the one that goes from H1 to A1 to T2 to T3. That's a path. Then there's a different path that goes H1 to A2 to C3 to B to R1. So you are steering little probes all the way through, and the red just happens to be you're doing the same thing from other sites. So for redundancy, you might want to have these are servers at the bottom that are doing these probes. Not just one server, but multiple servers per rack. Let's say 4, doing this, and they're getting evidence that there might be a problem on some link. You can do all kinds of things. You can have S1 talk to S5. You can have S1 just talk to itself. Send a packet going from H1 to A1 to T2 to T3 to C2 to A2 to H1 back to S1. You can steer the packet however you want. So it's distributed, massive scale, guided probes. And there's a very scalable, very universal way to do this, which essentially involves encapsulation and decapsulation, which is all in the earliest papers you see about VL2 and Monsoon and cross networks and all this stuff. So it's also in the load balancing papers. So you can use any protocol. You can use IP, GRE, MPLS to do encapsulation, decapsulation, and you can combine them. It's a very general idea, and it pretty much works on every switch we've ever seen. We use IP and IP because it's the simplest, most universal around. You could use VLAN tags or other things, or MPLS, and in fact, you might want to in some cases. Let's see. So here's an example. I have this S1 guy. He wants to send up to C1 at the top, from bottom to top, and that's a server at the bottom and a switch at the top. So it has an outer header and an inner header. It says, oh, I want to first go from S1 to C1. That's that yellow piece of the header. And then on the way back, I'm going to encapsulate my return path to come right back to me. So I'm going to tell, once I get to C1, that encapsulated inner IP header has C1 to S1. So the voodoo magic is you just put the packet in the network. It will swim up to C1, see if this is actually animated. It'll get there, and then it will decap. So you'll take off that yellow header. Now you've just got the inner header left, and now it routes back to the back to S1. So I've just created a guided probe in the network from a server. And I can stack this up, right? It doesn't have to be, here I talked about S1 and C1, and these are names of objects like switches and servers. I don't have to do that. I can talk about links. I can use private addresses. I don't have to use public addresses. There's a lot, it's very flexible. And it works just like data path source routing. So I can have here S1 goes to C1, and then now I'm starting to talk about links. X link goes to Y link, Z links goes to W link, and so forth. And I can just guide a packet all the way through. As a tool, that's kind of interesting, but what's really interesting is a continuous service. Make this thing work as a continuous service. So how does that work? So you have a controller that is assigning work to these net bouncer agents that are distributed across hundreds of thousands of servers. And that server, how does it learn what to do? Well, it knows, remember at the very beginning I talked about a graph? It knows the graph. So the graph service through other applications, this thing called NetBouncer Gin and scanlist.xml, it will inform the controller, here's my inventory I want you to scan, and here's your mission. Then the controller will then push that mission down to the NetBouncer agents. Then it'll probe the network. That's that blue arrow that goes up to the green cloud, probing tens of thousands of switches, then collecting all those data into basically a distributed bus that then puts it into a processor. We call it a NetBouncer processor. Goes to real-time analytics on the left, so you get alerts and analysis, automatic mitigation. And then on the right, you go to our large MapReduce service called Cosmos, which processes about 10 terabytes of this workload a day. That's where you pick up, okay, let's say there's a flaky link losing packets. Why? What kind of cable? Is there a trend here? What's the root cause? Is it craft error? What is bad batch? What is it? So through that offline analysis, you really get into the root cause and then solve the problem forever, after mitigating it on the analytics path. So here's an example. Again, these are tools we use every day, and these are real examples. I have many, many more, and I just picked a few for the talk. So here's a case where the issue is seen in ping mesh. Ping mesh detected an SLA issue. It only hit the scavenger traffic because it was congestion oriented, and the scavenger traffic takes the hit if there's congestion. Ping mesh is okay with traffic classes and ECN and all various flags on packets. But more interesting, NetBouncer found which link was having, or which switch and which link on the switch was having the problem. In this case, there's a bug in the switch firmware that causes polarization. You're supposed to spread the traffic evenly across lags or across ECMP L3 groups. And because of bugs, it did not do that. It sort of concentrated all the packets on one of the options, and that caused the drops. So first of all, you find it, you mitigate it. How do you mitigate it? Turn that switch off, or turn that link off. You have lots of switches, you have lots of links. It's okay to turn one or two off, 10% off. And then offline, through your data analysis, you figure out what's the pattern, and you fix the bug. That's the sort of life cycle and the data science of all this stuff, which we do every day. So how do these go together? What's the role of each one? A ping mesh really sees what the application sees. It sees TCP performance. It allows us to detect incidents and also give a severity impact to the incident. And NetBouncer, within 5 minutes or so, will localize the problem. And then together, you have localization and severity, which allows, gives you the right kind of safe way to respond instead of a panic way to respond. Now is this important? Let's respond quickly. If it's not so important, let's put it in the queue, and so forth. And that's what the automation does. So again, reliability is the coolest thing in networking, and developing rock-solid infrastructure is an amazing and challenging task. These are two of the tools we use in Azure data centers. They're based on the graph view. The thing about NetBouncer that's really interesting is it detects what we call silent drops. Lots of times, because of bugs and monitoring and just bugs in the firmware or bad links or other interesting things, you will get no alert, and yet packets are not getting there. 1 in 1,000 times, or and what's happening. So this will pick up those silent drops that otherwise you'd be doing some sort of binary search through your class network to find. You get timely alerting and mitigation. So this is running in all Microsoft data centers. One of the principles I often talk about is use the cloud to build the cloud. So we need big data to process this massive amount of monitoring data. Fortunately, we have a cloud. So we can use the big data and analytics from the cloud to, it's all there. And all the developers to create that stuff are all there, and the tools and the open source and so forth. So you can use that to solve the problem. This is, a stop along the way. The growth is amazing, and that's kind of what keeps us motivated and the juice is flowing. Is that in every dimension that we see, the cloud is growing. Data centers, links, servers, NICs, what have you, optics, and the workloads pouring in. So the stress this will put on monitoring, the stress this will put on control, management, V6, everything is very exciting. And we also believe in and see that all the new business is being born in the cloud from the beginning. And so you better solve that scale problem. And we're recruiting.
So we've got time for some questions. If you've got questions, we've got some runners with microphones coming around. So please use the mic so the folks on the stream can hear you as well.
Yeah, I have a quick question. I don't know if you mentioned in the presentation, maybe I missed it. I don't know if you can share a little bit of the remediation, how you fix, once you detect, how the problems are solved, what kind of automation you have, and maybe if you can quantify roughly how many of the incidents you're able to fix automatically, how many percentage-wise require human intervention?
Great problem, a great question. I think our mission is to mitigate. And if the mitigation is turning something down, you've got to be careful, because that's removing capacity from the network. So we have all kinds of checks where if something's flaky, we can turn it down, but not unless we've turned too much down and we have an isolation event. So almost everything I've talked about is automatically mitigated unless we have to make a judgment call, which is very rare. Now, having mitigated it, you need now to dig deeper into what caused this. And like the polarization bug, it's just bad firmware. So you ask yourself, how did that escape the lab? How did that get into my network? What's wrong with that? And then you go in. It's like the 5 whys. Understand how that bug got into the network and solve that. But when you have a polarization bug, which would never happen, you just fix it. Things like FCS errors, CRC type errors on links. Why do they happen? It could be and let me first answer, how long does it take to fix it? It depends on where that link is in your bundle of links. If you have, and how good your craftspeople are in cleaning and fixing links. We use tools like this so that bad, dirty links don't get out into the field. But if they do, then there's nothing you can do but physically clean them. And that becomes a more interesting problem. I was just talking with some colleagues at Broadcom. As we got 100 gig and 400 gig, they'll get more sort of the need for very precision crafts work for these high-speed links. A good person maybe can do 20, 25 per day. So you don't want to have that many such problems to escape your network, and you shouldn't, because the SLA on those links is pretty tough, pretty great if you actually install them correctly. Basically, I guess the answer is, if it's physical, you can take care of it quickly. If it's a bug, you have to fix the bug, and then it's just the life cycle of fixing and releasing.
When will all of this work on IPv6?
Oh, I don't think there's any problem with IPv6. Let me try to get you a more precise answer offline. I think there's no. We use IPv6. I just don't have that on the tip of my tongue. The answer to that.
A couple more questions.
Okay.
Oh, I had one quick question. I was curious the frequency with which ping mesh probes your network. So if you have any given path that you're probing, et cetera.
Where are you? Okay. Hi. Yeah. Frequency with which ping mesh did what?
So the frequency with which you send probes, let's say between any two machines.
Geez. Parveen, do you know? Yeah. So let me try to repeat. So as you go further out between, let's say, a server in this data center and that data center, you have to scale it down. In the rack, it's quite frequent. There is a SIGCOMM paper that describes some of that, which is probably fairly accurate. For us, investing in disk or storage for the purpose of reliability is an easy call. So we store all this stuff, and we analyze it all the time, because reliability is the mission. Even though you are filling up disk with ping data. Yeah.
All right, last question. Oh, you got a mic. And if you didn't get your questions, I think Albert's going to be hanging around. Other folks here, Parveen from Microsoft, and so during lunch and the breaks, try to catch them and ask the questions.
As you talk about your methodology for monitoring, it's mostly a polling-based model, right? It's a 5 to 10 minute interval you talked about.
Yes.
Right. Are you moving more towards a push model?
Great question.
From the server to the vendor switch?
Yeah. So, absolutely. So we like push for flow data, and we like push for counters.
Yeah.
And I didn't talk about counters, or I didn't talk about flow data. All I showed was a replicated. There's more to monitoring than this. Really, this talk was about net bouncer, these guided probes, where you have to inject traffic. But your first line of defense is the data that pushed to you from the switches. If you have a counter that says, "Hey, I'm broken," then you don't need net bouncer. So, that tells you a lot. And in fact, like a lossy link, you can see FCS errors sometimes in the counters. I guess the answer there is, you have this first line of defense, which is awesome in terms of push-based, pull-based counters and so forth, and logs. But at this kind of scale, it's going to miss. You'll still have the log that doesn't get to you. There's a bug in the switch, so the log doesn't get to you, or there's just a drop somewhere. So you have to have these additional mechanisms, or you're not going to get to the reliability you need, especially if the problem is high up in the spine, because it'll impact lots of different things below.
All right. Well, help me thank Al. Thanks, Albert. You have the clicker? Oh, his clicker's up there.
Yeah, let's go.
Great, cool. All right. So we're going to switch gears a little bit here. Who here has worked on wireless systems? wireless systems. All right, a good number of folks. Not a lot, but a few. So we're going to switch from the management plane. We're going to dive into some of the data plane, the wireless side of things. Going to bring up George from our Facebook team, working on one of the projects we announced just a couple of months ago, Terragraph, and he is one of the leads on that team, and we'll go over some of the challenges and the background behind that system. So please help me welcome George.
Thank you, Omar. So I'm George from Facebook. Trust me, it's really George. It's just spelled differently. I'm super excited today. First, I have such a great crowd. I'm first here for the first time on networking at scale. My background is electrical engineering, so I see probably a lot of folks from computer and science. I'm also very, very privileged today that I have a chance to speak on behalf of the whole Connectivity Lab on some of the really awesome stuff we're doing on communication system design and technology development on our mission to connect the world. So I want to give a big shout out to the whole Connectivity Lab team, a lot of smart people working diligently on connecting the world and building technology. I'm really just like a spokesman for the team. It still doesn't mean I'm a good speaker, so we'll come to that. So before we start with Terragraph, I just want to give you a short introduction about what we do at Connectivity Lab and how does this fit into a Facebook mission, and then where does the Terragraph fit into everything we do in our mission to connect the world. So this is the slide from Mark's keynote a few weeks ago. So he announced the 10-year goal for Facebook to give everyone the power to share anything with anyone. And he basically presented three main technologies that will actually enable that roadmap, and these are connectivity, artificial intelligence, and virtual augmented reality. So as you can tell, connectivity is an important part of our mission. So now, this is the world as we know it. It's basically people who have access to good quality internet with this is a cellular picture of 4G LTE connections and 3G connections. However, the rest of the picture is much, much grimmer. So more than 4 billion people in the world have no access to internet, and a large portion of the remaining people actually has access only to poor quality 2G connections. So at Connectivity Lab, our mission is to really connect the unconnected and improve the experience of the underserved. So we're really targeting this population here. Connectivity Lab was launched a few years ago as a lab to develop technologies that will actually reduce the cost of internet infrastructure. Our mission was to actually improve things by order of magnitude so we can reduce the cost and reach populations where current solutions are not economically viable. We are not planning to run these networks by ourselves. We're going to develop technology, advance it to the level where it's basically economically viable for our partners and vendors to go and operate, but we'll just make sure that the benefits that we bring actually translate to the end people. So now let's look at the technology side. With the help of data science and AI teams and Facebook, we quickly realized where the people live, right? So and we saw that density population spans 2 orders of magnitude. So it's quite obvious that one solution doesn't fit you all. So to break up the problem, we identified low density population, medium density population, and the high density population. In the medium to high density population, the main problem is really no connectivity. People just simply don't have anything to connect to. And this is where our solution is actually beaming the internet from the sky, from satellites, and the UAVs. On the high density population, which is anywhere from the dense urban, let's say up to the rural, there is connectivity, but the problem is the quality of connectivity is not good. So this is where we're actually focusing on the terrestrial side, and we recently announced 2 projects there, the Aries and the Terragraph. I'll be speaking about Terragraph today. Before we really dive into the Terragraph, I just want to give you a little bit of picture how these systems works in real world. So this is the part of our 96 element antenna for the Aries project. It's basically high spectral efficiency, high energy efficiency system for future wireless communications. This is the microwave frequencies. Free space optics links, 10x improvement in throughput, let's say connecting the UVs above the weather. Most of you have seen the picture of our Aquila airplane. It's a long endurance solar panel plane. The wingspan is larger than 737. It flies above the weather, 60,000 feet, let's say twice the height of the commercial air fleet. Finally, we also announced that we are launching some of the satellites for the regions with very low density population, like sub-Saharan Africa. That was for the Mark's press a few weeks ago. So that's about Connectivity Lab. We're now diving into the telegraph portion, which is the main part of my talk. So this is the outline. I'll first give you a perspective, what is telegraph, and now also give you a little bit hint about what are the technical challenges that we run into where we're developing the system. I will highlight a couple of the breakthroughs, and then we'll actually wrap up with some of the performance. So what is really a telegraph? As we've already seen, it's a terrestrial solution for high-speed internet connectivity in dense urban areas. It's a 60 gigahertz multi-node wireless distribution network. It's optimized for high volume. It's utilizing off-the-shelf ViGig components. It's leveraging the cloud for intensive data processing and the self-organizing network. And the core part of the system designed for ease of installation and mounting on street furniture. So that's also very important for us. When we talk about street furniture, we think about lampposts, traffic lights. So when you develop a system, a wireless system of this scale, it's always difficult to find places to mount it. And we're actually looking at ways that with the one license, we can actually get access to a lot of street furniture in the streets. So this is how our network works, the looks, and when deployed on the street level. So we really have two types of nodes. We have the distribution nodes, which are mounted, let's say in this case, on the lamppost. They have anywhere from 2 to 4 radio sectors, and they form our basic trunking topology. So basically, that's the core of the network, distribution network. Then on top of that, we have client nodes, which are mounted typically on the side of the streets, and they are single radio sectors which connect to the distribution nodes on one side, and on the other side they provide internet, either for Wi-Fi access points, for cellular small cells, or just for internet for the end user or the curb of the building. So now, why building a new system? What's wrong with existing solutions for the last mile distribution of the internet? So we looked at what's there, and we identified the usual suspects. You have copper, fiber, and a cellular. So let's go one by one. Copper, limited bandwidth. That's your DSL cable modem. At some point, you run out of speed. Fiber is great. It really offers 7 megabits per second to meet this multi-gigabit demand. It's present in many places. It's just not present where people need it. So how to get fiber to the end user? You need to dig the streets. You need to put optical cables. It's not really practical. It's very expensive to do it in the urban areas and high-density urban areas. So we pass on that. Finally, cellular. It has a great technology potential, but it's impeded by lack of spectrum. Most of current cellular systems, they operate in licensed bands. The spectrum is not available. It's expensive. It's just not enough spectrum to meet this high demand. So we are engineers. We like to think about orders of magnitude. So we ask ourselves, can we really build a system which has a fiber speeds, but it basically deploys and operates at a fraction of the cost? And that's how we came up with Telegraph. So I just want to give you a little bit, let's zoom into the spectrum, because we identify spectrum as an important aspect of what we do. This is the US radio spectrum allocation, anywhere from 3 kilohertz on one corner all the way to 300 gigahertz on the other side. This is a logarithmic scale. So basically, every row is 1 decade. So the first row is 3 kilohertz to 30 kilohertz, and then second row is 30 kilohertz to 300 kilohertz, so forth and so forth. So basically, you come to the last row, which is 30 gigahertz to 300 gigahertz. This is really important spectrum. This is where most of the current integrated circuit research is ongoing today in the world, and this is basically the most promising part of the spectrum for future high data rate communications. Why is that important? Because there's abundance of spectrum in that area. And there are already systems which operate in this area, and most of them are actually licensed. So you have, for example, Ka band, which is anywhere from 26.5 to 40 gigahertz, which is used for commercial satellite systems. You have E-band on the other side, 70 to 90 gigahertz, which is available for fixed wireless outdoors. You have 28 and 38 gigahertz, which are now being eyeballed and for a 5G cellular. You have 77 gigahertz, for example, vehicle radar. And then there's this important part, which is 60 gigahertz. So out of all the spectrum of millimeter wave, 60 gigahertz is basically unlicensed today. And we will go back later into propagation, and we'll give you a little bit, hints why it's actually turned out to be unlicensed. What is very important is that because this is a logarithmic scale, if I put things in perspective, and you look at all the spectrum which you use today in your everyday life for AM, FM radio, for all of your cellular from 2G, 3G, 4G, LTE, all of your TV broadcast, Wi-Fi, 2.45 gigahertz ISM band, you take all this together, and you actually have less spectrum that is available in this 60 gigahertz unlicensed band. So it's really awesome. Another view to the thing is that if you look at the LTE today, let's say release 11.12, which is not even in your phones yet, typical system band is 20 megahertz, but you can do carrier aggregation. You can get up to 5 carriers, so you're looking at maximum 100 megahertz. In 60 gigahertz, there are 3 or 4 channels, depending on the side of the world, which each is 2 gigahertz wide. So today, we are already using 20 times more spectrum than is actually LTE will ever use when it basically comes to its fruition. So that's the spectrum picture. That's when part side. Again, we'll come back to 60 gigahertz and why is it unlicensed later. Now, millimeter waves, first of all, this last row is a millimeter wave. Why is it millimeter wave? Because simply, if you do the math from 30 to 300 gigahertz, the wavelets are anywhere from 1 to 10 millimeters. That's very important later when we come to antenna design. So it's the most promising enabler for future wireless communications, and what's also important that several industrial standardization efforts already kicked in that area, and most important one is basically WiGig on 802.11ad, which is basically continuation of the 802.11ac family that all you're probably familiar with. And as a result of that, we're already seeing actually chips on the market from both baseband and RFIC, which are designed for this standard. Now that's very important because we don't want to start building chips. We want to actually use that rich ecosystem and put in perspective of future communication design. So now the challenges. So these are the main ones that we actually run into. First of all, the 60 gigahertz band is deemed unsuitable for outdoor communications due to high oxygen absorption, rain, fade, and triatunation. If you remember the picture from the previous slide, it was giving a use case for 11AD, which is the short-range indoor communication. You're sitting indoors, you're beaming to your TV at high data rates, and those systems are really designed to complement the existing 11A CNN, where you basically have a coverage, a nominal data rate with 11A CNN, and then opportunistically, when you're close to your device, you can actually beam at very high power and very high speed. So now we're putting that, and we're actually going outside, and we're trying to apply this to outdoor communications and bridge the long range. So that was the first challenge. Second challenge is that it was a layer 2 protocol for MAC in the CSMA. As all the other 11N protocols, it actually relies on CSMA, and which actually has very poor efficiency in multi-hop networks. Finally, we actually run into lack of easily extendable routing protocols for fast link recovery in the large multiple wireless networks. So now let's look at the band that nobody wanted. That was the 60 gigahertz band. So this equation basically describes pretty much any wireless propagation with any frequency. So PR and PTR receive and transmit power as measured milliwatts. This is a logarithmic domain, so it's basically dBm. Just to calibrate, this system typically emit anywhere around 43 dBm, so that's about 20 watts. So this is the transmit and receive power, and then what happens in between, we'll skip just for a second, the GR and GT, is all these negative terms. They're negative because they attenuate your signal. They basically reduce the energy as the signal comes from transmit to the receiver. So the first one is the free space propagation loss. What we see there is that energy drops as a square in proportion to the distance between transmit and the receiver, as well as a function of the frequency. So as you go to the higher frequencies, actually there's more propagation loss, right? Just the free space propagation loss. And then we have several terms on the right side, which is also negative. You can group them in a different way, but we group them in a way to emphasize the importance that it has to 60 gigahertz of propagation. First one is oxygen absorption. Second one is the rain, and the third one is general fading propagation, which is anyway from reflections or foliage, going through foliage. Again, diffraction is not what we have at 60 gigahertz. which you normally have at the microwaves. So now let's go one by one. Now this picture is really telling why is this the band that nobody wanted. So if you look on the right, this is basically oxygen absorption as a function of frequency. So there's this huge peak, which picks up somewhere around 42 all the way to 57 gigahertz, where basically oxygen absorption grows from 1 dB per kilometer to 15 dB per kilometer and comes back. So what's really happening there, linear scale, 98% of energy actually gets absorbed over 1 kilometer of propagation. So apparently this phenomenon is well known, and physicists actually already explained it. It was due to a Nobel Prize laureate, Professor Van Vleck, who actually unveiled this back in 1947 in his paper. The oxygen is a paramagnetic, so it means it's a magnetic dipole. And in general, magnetic dipoles actually has much less absorption of electromagnetic energy than electronic dipoles. However, that's true unless you hit them with their resonating frequency. And it turns out for oxygen molecules, the resonating frequency is 60 gigahertz, so we're just out of luck. So what it means is basically as the electromagnetic waves go through the air, it hits the oxygen molecules, and the electrons actually move in the same electron state. They resonate, they absorb the energy. So what can we do? We can actually license all of the spectrum and then give